Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 64 and this is also going to be tutorial number 18. So we shall be continuing from where we left, and that's why I've retained the last part of the previous lecture, but I call this page number 1 for this lecture though, please don't, okay? So then we were discussing about the term symbol, the idea of a term symbol, and I was telling you that each electronic configuration could be uniquely mapped with one term symbol, one specific term symbol notation. So, and we discussed that the ground state term symbol for the oxygen atom is what? Is going to be triplet P2, right? So triplet P2 is what we had written the term symbol to be. Now, but if we consider an excited state electronic configuration, that is, let's say that this specific electronic configuration of oxygen, 1s2, 2s2, 2px up down, 2py up, 2pz up. Let's say it goes to this upon Now you can ask me, upon electronic excitation, why should this happen? Why can't it go to a 3p the 3s orbital, etc., etc.? Of course anything can happen, as it turns out that this is what is happening experimentally, okay? The reasons for it we shall come and I'll tell you very soon, okay? But then, so what's happening is that upon electronically exciting this ground state configuration, right, which was in accordance with your Hund's rule of maximum multiplicity, etc., that gets changed and you go to this configuration, okay, right? So let's now obtain the term symbol corresponding to this specific configuration, okay? And so the term symbol for the excited electronic configuration of oxygen is going to be again 2s plus 1 Lj, right? Now the capital S here is going to be what? Oh well, this of course completely paired, so no need to take them into account. And for these, this is paired, and there are no electrons here, correct? So therefore this is going to be S is equal to 0, and therefore my spin multiplicity is therefore going to be 2 times 0 plus 1, 2s plus 1 is equal to 1, right? In other words, we get what is called as a singlet state. Having done that, what about my L value? Now, my capital L value is going to be in the same way, right? We have to add all the M-symbol values for all these electrons. So it is going to be for this particular case. So again, we're not taking these into account because the M-symbol value is going to be 0, right? So we're just going to be taking into account these three, the L value is going to be 0, okay? The L value is going to be 0. So we shall be only considering the M-symbol values for the p orbitals, okay? So for the 2p, this is going to be plus 1 for the 2px, the 2 electrons over here, right? Plus 0 for the 2py electrons, right? And there were no electrons here, so nothing to take into account. So this is going to be 2, which is denoted by the symbol we saw here, right? Somewhere in the previous lecture. For capital L is equal to 0 corresponded to a capital S, and capital L is equal to 1 corresponded to a capital P, and capital L equal to 2 corresponds to a capital D. So therefore, my 2s is plus 1 is going to be 1, and my L is capital L is going to be D, and J is what? Is again going to be L plus S, which is going to be 3. Are we clear, right? So this specific state, okay, right? So this specific electronic state, the term symbol is going to be what is called as, I'll just write it here. So the Ts for the excited electronic state of O can be written as 1d3. Of course, in some cases, a slight modification to this tree may also be needed, but let us just leave it at this right now. Okay, right? So the electronic configuration of this is 1d3. Whereas for the ground state, what did we see? It was triplet P2. So this is 1d3, or in other words, this is actually nothing but a singlet state. Okay, whereas the ground state corresponded to a triplet state. Okay, so what have we done so far? I've given to you two illustrations, okay, right, of various term symbols, right? Various term symbols which could be mapped uniquely with a given electronic configuration. Now these term symbols are going to be used in the selection rules. Before seeing how, I'll just give you a quick homework, okay, right? I'll give you a quick homework. The homework will be that show that this specific electronic configuration, that is for oxygen 1s2, 2s2, your 2px up and down, 2py up, and let's say 2pz down. This configuration, okay, let's say this one, 2px up, 2py up and down, and 2pz, let's say, is up. Okay, right? See, some electronic excitation can also lead to this, right? Such that the m symbol values are going to be +1 here, 0 over there, and -1, right? Corresponds to some kind of a, let's say, it corresponds to a singlet S state. Right? In other words, show that the term symbol for O corresponding to this electronic configuration is singlet S. Don't worry about the J. You can of course find out the J, but show that this corresponds to a singlet S state. This is homework. It's a straightforward exercise, and based on this, right, what I illustrated to you with the oxygen, you can carry it out for all the atoms, and you can now given any unique electronic configuration. When I say a unique electronic configuration, I'm talking about an electronic configuration which takes into account the spin pairing also. All right, not simply writing 1s2, 2s2, 2p blah, something like that. Okay, right? Given an electronic configuration, one unique term symbol can be associated with it. All right. So now that I've given you some examples, right, you can get the term symbol for any atom. Therefore, although I must tell you that the moment you go to the transition metals, etc., you have to be associated with d electrons also, correct? And once we associate with d electron, the total number of unique electronic configurations is going to be very large, and so therefore the total number of term symbols associated are also going to be very, very large. Okay, please keep note of this. That's all. Okay, so now having understood the idea of term symbols using an illustration, let's see how these term symbols are used in the selection rule. Okay, so the term symbols in the specific selection selection rules, the term symbols in the specific selection rules are going to be as follows. Now, having written, so the idea is to first understand what electronic configuration you're talking about, and having understood the electronic configuration, you map it with a unique term symbol. Okay. Now, having obtained a term symbol, next, your task would be to use the term symbol in the specific selection rules. And how do these rules come about? Well, I'm repeating myself for the umpteenth time so that you don't get lost. These selection rules are coming from the computed transition moment integral. How exactly it is computed, we don't worry about, because that involves some quantum chemistry and math, which we ignore for the purpose of our class, because we have to cover so much more content, more directly related to astrochemistry. Okay, so I'll just take that for granted. But by computing the value of the integral, you will mathematically see that these selection rules will be applicable. Okay, so the selection rules are going to be that. So in the course of any electronic transition, right, number one is that your delta S, okay, delta capital S should be 0. In other words, the spin cannot change. All right, so this is the your delta capital S should be 0. This is one selection rule. The next selection rule is that your delta L can be 0 or plus minus 1, right? So this is the net. When I say SL, I'm not talking about this small s, small l. I'm talking about capital S or capital L. Okay, please note that. So my capital delta L should be equal to 0 or plus minus 1. And noting that L equal to 0 to L equal to 0, not allowed. Okay, the third one is that my delta J should be equal to 0 or plus minus 1 again. And again, the point is that my J equal to 0, not allowed. Do you understand why there are two different L's and two different J's here? I'm talking about the L for, let's say, state 1, initial or final, to some other L value. Here also, therefore, you get two L values, two J values, okay, right? So these are the selection rules for electronic transitions in atoms, all right? But note yet again, these selection rules, where are they likely to be more applicable, on Earth or, in space? As we've been discussing all along, in space, we have a lot of time for transitions to happen. So these electronic the selection rules are much more applicable to what's happening on Earth, okay, than its relevance to space itself. Point number one. And point number two, let's say that the selection rules are violated. Okay, let's say, for example, in an electronic transition, the selection rules are violated. Do you think that transition will happen or not? Remember what I told you. Again, go back to lectures 45 or 46, where I gave you a big picture hint. Of course, the transitions will happen, right? For reasons, like beyond the scope of this course. For example, there are other modes, modes called as spin orbit coupling, relativistic effects will come into play, etc., etc. So by other modes, beyond, these selection rules, some transitions will still happen, but only that the intensities of those lines will be small, okay? So satisfying the selection rules implies that we'll be getting a more intense signal, right? And the violation of the selection rules imply that the signal is going to be significantly less intense. In some cases, the intensity can also be augmented by other technical means beyond the selection rules themselves. All right, so that's it. So what did we see so far? We have looked into the selection rules for electronic transitions in atoms. Okay, and now are you able to fully comprehend what I said much earlier? When I was giving you a big picture introduction to selection rules, perhaps in lectures 45, 46, 47, somewhere around then, I told you that the selection rules can be expressed in terms of quantum numbers. In the case of rotational and vibrational transitions, we express them in terms of the rotational and vibrational quantum numbers. Whereas in the case of atomic transitions, we are expressing them in terms of capital S and capital L and capital J. Correct? There is, of course, I must also point out one more thing. There is one more selection rule concerning the wave function. I'm just skipping it. I'm skipping it in this course because I haven't told you much about, the wave function and its properties. Okay, so don't worry about it. For now, just I realized that there is something called as selection rule, and they tell you about the intensity of the spectral line obtained, and that it is going to be much more applicable on Earth than it is, for transitions happening in space. All right. Okay. So that said, I will now briefly, connect the concept of a term symbol for atomic transitions with the term symbol for molecules. Okay. So our next aspect is going to be connection between atomic and molecular. When I say molecular, it's easier done for diatomic species. Diatomic term symbols. Remember, all this started as part of the question asked in tutorial 17. And in that question, I told that, well, after addressing this question, I'll also briefly address the connection between the atomic and molecular ones, right? Okay. So we'll do it as follows. Okay. So the term symbol for an atom is given by what? By 2s plus 1 Lj. By the way, this is what is called as the LS coupling, right? We have the capital L and then the capital S, and we take into account its coupling. Okay, right? So this is one way to understand the idea of a term symbol. It does exclude some effects such as relativistic effects, which is why the selection rules are not complete, as I told you earlier. Okay, please be aware of that. All right. So this 2s plus 1 is analogous to what is called as 2 sigma plus 1, right? Capital lambda, capital omega. So this is for atoms, and this is going to be for molecules. Now, so the S is equivalent to sigma, and your L is equivalent to lambda, and your J is equivalent to omega. Okay, right? So please understand that the way in which you get S and sigma is going to be the same, but the way in which you get lambda, right, that actually depends on the actual molecular orbital configuration. Okay, the configuration of in which the molecular orbitals are arranged. You've all heard the phase molecular orbitals, right? We're talking about the idea, the theory which explained why O2 is paramagnetic, for example, right? Recall from your 11th and 12th standard. So the equivalent of L is going to be lambda. To get lambda, you need to know the molecular orbital, the electronic configuration as per the molecular orbital theory. Okay, and of course your capital omega is nothing but synonymous with capital J. But in addition to these things, okay, right, in diatomic molecules, see, atoms have spherical symmetry, correct? Even though we cannot exactly visualize an atom itself, right, based on quantum mechanics, atoms have spherical symmetry. What about diatomic species? They have cylindrical symmetry, right? An atom, you extend it, you kind of get diatomic systems. So reflecting this the cylindrical nature, right, you also have two other modifications to this term symbol. You also use your plus or minus, like a notation here to talk about the reflection symmetry of the wave function. Okay, reflection symmetry of the wave function, right? And you also have here two subscripts called as G bar U, okay, right, to represent the symmetry of the wave function. That's it. Okay. Now, we do not have a lot of time to go through all the aspects of molecular term symbols, especially diatomic term symbols, okay, and of course polyatomic species also, because I have to start with molecular orbital theory. You should know how to write the electronic configuration, and there's a small variation there. Then I have to teach you about the parity of the wave functions, which is symmetric, which is not symmetric, etc., etc. So all this is a bit tangential to astrochemistry. The first course in astrochemistry. Of course, it is important in astrochemistry. So what I'll do is, I will just tell you that, okay, the notations are going to be expressed in Greek and Latin instead of simple English, okay, right, for the diatomics. And also, see, sometimes to also get your the exact lambda, right, you also need something called as group theory, okay. So that is also going to be beyond the scope of this course. So I'll just leave it at this. And please understand that whenever sometime, for example, in papers, right, in papers and literature articles, you may be seeing, some Greek and Latin symbols in the context of transitions, electronic transitions. Please understand that they're talking about the term symbols corresponding to different electronic states. For example, okay, if you consider the O2 molecule, if you, for example, consider the O2 molecule, let's say, this is for O atom, right? The triplet P2 state, right? That corresponds to what is called as a triplet sigma G plus, okay, right? So this lambda, okay, right? This lambda, just like this L can have like various values, your SPD, they are going to be represented by sigma, pi, delta, etc., etc., okay? So the lambda value is going to be sigma, right? So this is going to be the ground state, and by some fundamentals of molecular orbital theory, you can also see, why this and this come up, okay, right? So, and similarly, the 1D, if I correct, yeah, the singlet D3 state, right, for oxygen atom, right, is represented as something like 1 delta G, okay, right? Now, don't ask me why there's a P here, but there's a sigma here, okay? That can be easily understood by using molecular orbital theory, but we're not going to go there, okay, right? So this is going to be the ground state, and this is going to be the first electronic excited state. I'm just giving you illustrations, and also note that in some cases, right, in some cases, the reflection symmetry of the wave function matters. In some other cases, it does not. I'm just giving you these things to tell you that be aware. So be aware of molecular, especially diatomic term symbols. Broadly, probably I would require 1 or 2 lectures exclusively to teach how to write these specific term symbols, but I'm going to skip it in the interest of many things, many other interesting things which are more directly concerned with astrochemistry. Okay, right? That's it. So where are we? We are at the stage where we understand the selection rules for atoms. Similar selection rules based on the term symbols for molecules can also be written. Okay, that's it. And the next time you see some Greek letter corresponding to an electronic state for molecules, please understand that it's analogous to what is done for atoms, just that it's a little bit more complicated. Now, beyond atomics, it gets really complicated because we really have to understand group theory, what are called as the character tables, and then you should do some matrix multiplication, etc., to get the specific state of polyatomic molecules. That is definitely beyond the scope of this lecture, but get the broad picture. Get the broad picture that every time somebody is talking about a specific electronic state, please understand that it corresponds to one given electronic configuration. In the case of atoms, it's the electronic configuration of atoms. In the case of molecules, it is one specific molecular orbital, the electronic configuration based on molecular orbital theory. All right, that's it. So I end our discussion on term symbols and selection rules at this stage, and I'll go to the next problem of this tutorial. Are we clear? So do understand with this, like the discussion on selection rules in this course is complete. Okay, complete for this course. Although note that there is so much more to learn. For example, how to get these and how to use them, etc., etc. We're not concerned in this initial course. In a course devoted to molecular spectroscopy, we can definitely discuss these at great length. All right. On that note, I put an end to this chapter, and I'll be going to the next question for this tutorial. It is, now, see, the next aspect, is going to be a clarification actually. Thanks to some questions raised, okay, right? A clarification all the way from lectures 43 and which is also connected with lecture 53, okay? Please note this, okay? So I request you to go back to lectures 43 and 53 for a brief moment to spot the connection, okay? The question is as follows. In lecture 43, I had written one equation called as BB. U, this is based on the black body radiation. U is given by something like 8 pi divided times 1 by e to the power h nu by kBt minus 1, right? So this is 8 pi h nu cube by c cube times 1 by e to the power h nu by kBt minus 1. Kb is Boltzmann constant. and 1 is not in the exponent. Please know that. Okay, it is in the base. Okay, this is kBt, 1 by h nu times kBt minus 1. This is equation BB. Okay, now in the same lecture, we also had one more equation called as equation BU. Equation BU was written such that my U was something like A21 divided by G1 by G2 times e to the power minus h nu by kBt minus 1. Sorry, minus B21. Then I kind of modified it. Okay, I modified it by dividing throughout by B21. Okay, by dividing throughout by B21, such that I have the expression after modification, right? I got this, and after modification, after dividing throughout by B21, we get this as A21 by B21 divided by G1 by G2 times e to the power minus h nu by kBt times 1 by B21 minus 1, right? So this is what we had. So we started off with this equation, and then I divided both sides by B21, right? Divide this by B21 and divide this by B21 also. Now then what I did was, in lecture 43, so then what I did was, I was comparing, this with this, and I was telling that the denominator looks the same, right? But some sharp eyes did catch that there is a positive sign here, but there is a negative sign here. So how can I even compare the forms, correct? Do you understand the confusion? And that is where, I had forgotten to give you a nuance. Okay, it is that when I write it this way in equation U, when I write it this way, right, my delta E is equal to h nu, but my delta E is defined as E2 minus E1 conventionally, right? So that is how I get this h nu here. So this plus h nu comes from E2 minus E1, all right? But this minus h nu, right, in expression U comes from delta E is equal to E1 minus E2, okay, right? As I illustrated in lecture 43, as I clarified in lecture 53, sorry. Because in lecture 43, I never told you what my delta E is going to be at all, okay? It was only in lecture 53 that I clarified that my delta E, right, is going to be defined in this expression as E1 minus E2. Because here delta E is E2 minus E1 and delta E here is E1 minus E2, right? This positive sign and negative sign can be compared, because ultimately we are comparing e to the power delta E, delta E by delta E divided by kBt minus 1, all right? So that is why we were able to compare these two expressions, right? Even though there was these two expressions, not this one, okay, after dividing by B21 in lecture 43, even though there was a negative sign here. That is because we were inconsistent in our use of delta E's. But once we, correctly define delta E's properly, right, this comparison becomes meaningful. So with that, this clarification is also sorted out. So I hope, with this, we come to the conclusion of this tutorial. And as always in a tutorial, we not just look into new problems, such as, for example, selection rules and term symbols and such ideas, but also clarify existing, existing doubts and questions, and also any inconsistency that I may have done. Okay. So on that note, I end this tutorial 18 and lecture 64. So in lecture 65, which we shall be looking at some cool aspect associated with the astronomical side of astronomical spectroscopy. On that note, you have a great day. See you in the next lecture.